The next big idea here we looked at here was fusion. Remember, both fission, breaking up larger things, fusion is joining together lighter things. Both of them increase the binding energy. Both of them will actually release energy. So in this case here, fusion produces products that are heavier. In this case here, the heavier things here have a higher binding energy per nucleon. They're more stable, so we can harness the energy. Unfortunately, fusion reactions, even though they are very promising, the fuel is really inexpensive. We can use standard hydrogen sources, oxygen sources, really abundant. I don't need to transport them around. There's not a lot of waste radioactive material that's produced. This one here is the holy grail if we can somehow manage it. However, we're going to see in this section here the only successful case of fusion, because we need such intense temperatures. We actually need to sustain a plasma for long periods of time. It hasn't been able to been very economical yet. We can actually just look in into the stars. Stars actually do this fusion to actually generate the solar radiation that we use later on. So for stars here, a successful fusion reactor, we actually have majority of stars here are primarily hydrogen. Some of them have helium. Helium is sort of the outcome of hydrogens being fused together. Now stars have a whole host of other elements as well, but the majority are the hydrogens and heliums. The stars are so far away. How do we know what the stars themselves are made up of? If you remember back in our chapter 2, chapter 3, we can point what's called the spectroscope here. We can look at the absorption spectra, what colors of light are actually being absorbed away by the chemicals, or even the emission spectra. When those excited electrons fall to lower gaps, when that energy gets released, what energies are actually being released off. That's how we tell not only which elements are present, but also how abundant the chemicals are. So every element itself has different size discrete gaps, different size spacings. So this absorption spectra, emission spectra becomes like a fingerprint for the element there. All right, so back to the Earth example here. Whether we somehow in the future harness fusion or just look at our fission products here, radioactive waste here, they may have isotopes that have either long or short half-lives. Make sure you know the definition for half-life. Half-life is the time it takes for half of the samples to decay, from the radioactive, from the active form to the less active form. We talked about 3 forms of decay last year: alpha, beta, gamma. Alpha particles are helium nuclei. These ones here are the weakest. They can be stopped by a simple piece of paper. Doesn't take much. These are the ones that Rutherford used to shoot at a gold foil, looking at the deflection. Beta particles are electrons, but these electrons come from the nucleus. That's why it's a nuclear reactor. These ones here are about 100 times more penetrating than alpha. It takes a couple meters of air. If I have different materials, this one here can soak up the beta particles here, no problem. We go alpha, beta, gamma is the highest intensity. Gamma is just pure energy that's being released. This one here is yet another 100 times even stronger than beta. In this case here, we need heavy-duty lead to actually contain some of that radiation. So in terms of storage and disposal, when I have all this waste out of a nuclear power plant, what do I do with it? It's going to depend on what type of radioactivity, alpha, beta, gamma, how much am I producing, as well as the half-life. Turns out a lot of our radioactive waste is referred to as low-level waste. This is 90% of all the waste that we have. 90% actually contains the low-level radiation, only 1% of radioactivity. This one here can release low-energy alpha, low-energy beta, and this one here is like, oh, when I was working with this nuclear material here, maybe I was wearing a lab coat or I was wearing gloves here. Those ones inevitably will get contaminated by the nuclear sources, but they contain really trace amounts of nuclear energy. So depending on the radiation level here, this one here can even be stored on site until it's safe. We just sort of wait out its half-life, or bury it in shallow pits here. We don't really need really intense treatment. High level waste in contrast here, we don't have a lot of it, but this one here really would be the moderators and control rods here inside our power plants. This one here, I don't have a huge fraction of it. However, it contains a majority of the total radiation. The main sources here are going to be, again, spent fuel rods when I need to replace those ones. We really haven't found a good solution for this one here. So mainly what we've done is we've just said, oh, let's just dig a deep hole. Let's vitrify them. Let's solidify them in glass, solidify them in concrete. Let's bury it really deep down and let it wait out the millennia. I know it's not the ideal solution, but that's sort of the only solution that we've come up with so far, because some of these have half-lives on the order of millions of years, again, not on our time span of humans. The next energy source here we looked at mainly was solar energy. In fact, all of our energy ultimately does come from the sun. If you contrast nuclear power plants here, remember every time we do a conversion, nuclear to heat, heat to kinetic, kinetic to electrical, we're going to always be degrading the energy source. The efficiency is always going to be less than 100%, typically about maybe 20-30% or so. If I contrast this slide here with a solar design, a solar design here is able to provide the electrical energy, convenient for storage, convenient for use. It's actually able to convert light energy directly into electrical energy. The less transformations that I need, the more energy I can actually keep to myself. So we're going to actually engineer solar panels as photovoltaics. They take light energy, they convert into electrical energy, and we actually generate a DC, an electrical current. We started off looking at plant cells. So plant cells undergo photosynthesis. They take atmospheric gases like carbon dioxide and water. They endothermically absorb that light radiation. They end up producing high energy sugars. In this case here, it's just glucose. And in this case here, us as consumers, we end up eating these plants here, or we eat the animals that eat the plants here. Inside our bodies, it's like a mini sort of burning reaction. We're not setting a fire or anything, but we are somehow combusting these ones here in a process called cellular respiration. We're releasing off the carbon dioxide and water, and we're able to utilize that energy for our normal metabolism, normal body functions. How do plants harness this light energy here? Plants undergoing photosynthesis. If you look at the plant cells themselves, plant cells have a unique structure called a chloroplast. Chloroplasts here are really easy to recognize because there's these little plates here. I believe these are called stoma. The stoma here actually appear green to us because the chloroplasts themselves contain a molecule inside called chlorophyll. Remember from chapter 3, the reason why something looks green is not because it absorbs green, it's because it absorbs everything except for green. So in this case here, it absorbed more so the reddy, orangey wavelengths. What's the chemical feature that allows the chlorophyll molecule to actually absorb this visible light color? The chemical structure is actually a conjugated electronic structure. So here's some examples of some molecules here. The conjugated electronic structure here is this notion of having alternating single and double bonds. In fact, the longer, the more extensive this conjugation, the less energy that's needed to actually excite these electrons to actually absorb this radiation, so we can actually absorb a higher wavelength light. So this is the chlorophyll molecule here. We call this part here the porphyrin ring. We see definitely there's a lot of that double single pattern that we see. So this energy here, the solar energy that strikes the chloroplasts here, they excite the pi electrons. They excite them into the pi star state. As your conjugation increases, the amount of energy needed to that excitation actually decreases. So here we have going from ethene, which is one double bond, to a longer conjugated system going downwards. We steadily need less and less energy. Once it starts absorbing the visible, it absorbs one color, and we're going to see the complementary color being released. For these plant cells here, we then mimic later on with DSSCs, with photovoltaics. Let's just switch over to look at biofuels before we do that. So for biofuels here, I can take those sugars, I can definitely metabolize them, I can do respiration on them directly, or otherwise what you can do is you can treat them. In this case here, fermentation, I can ferment glucose into ethanol. Ethanol here can be used as a biofuel. Ethanol is produced as a lot of, it's a waste product in a lot of other industrial, agricultural reactions. So if I can somehow harness the ethanol, somehow harness this biofuel, I can actually use the biofuel as a gasoline source. I can use that straight up. However, we're always talking in this section here, what's the advantage of doing one way, what's the disadvantages? In this case here, the advantage of using biofuel, it's a lower greenhouse emission. Because the ethanol otherwise would have taken from photosynthesis, the glucose molecule stole carbon dioxide, put it in glucose, the glucose got converted over to ethanol. Any ethanol that gets burnt and released carbon dioxide would have just been carbon dioxide that the plant cells originally absorbed anyways. That's why we refer to them as carbon neutral. It reduces our dependence on oil. Anytime you have an alternative source here, it lessens our dependence on our current sources. Disadvantage, however, we talked about two ways of quantifying the energy that's given off here. We can talk about specific energy, the energy per mass or energy density, energy per volume. In fact, about 1.5 liters of ethanol is needed to produce the same amount of energy as 1 liter ethanol. So that's a lower specific energy, lower density. You need more of it, burn more of it to actually release the same amount of energy that we need. And it can also cause potential damage to engine. Ethanol here has hydrogen bonding, so it can absorb the moisture from the air, leading to corrosion. there's typically a high energy cost of production. So in you trying to convert it to glucose and then convert it to ethanol here, it could actually amount to the same carbon footprint as using gasoline directly. Of course, if ethanol was produced as a waste, we're just being able to recycle that waste. That's a different story. I like this sort of food versus fuel debate here. Basically, the notion here is if you are growing crops here not for the purpose of eating or food, it's actually being divvied off, it might actually drive up supply and demand. Poorer countries might actually choose to export their corn instead of actually using it for food sources. They're actually using it to be converted to fuel sources. Energy content of vegetable oils is similar to that of diesel fuel, so it is comparable. However, we do need to modify our combustion engines so that they can use it. We're going to see that diesel fuels or biofuels here typically are way too viscous. Let's look back at that fractionating column. Fractionating column here, we were looking mainly at the C5s to C10s. Diesel fuels here will primarily look at a little bit heavier fuels, so we're looking at that section there. The gasoline is going to be sort of the top, so C6 to C10. Diesel fuels, biofuels here like ethanol here are typically going to be slightly longer chains. I mentioned ethanol here is typically a waste product, or diesel fuels are typically waste from other processes here. We're going to take a look at a vegetable oil. So vegetable oils here are made out of glycerol. They have long fatty acid chains. Those 3 fatty acid chains are stuck on the same glycerol molecule. In this case here, our vegetable oil, similar to other ethanol and other biofuels here, they typically have this structure. They have all these long R chains, all these chains here which will interact really high London forces, and that's going to actually amount to this oil here being very sticky. So if you imagine taking the vegetable oil without treating it, if you stick it into the engine, it's going to gum up your engine really, really quickly. So in this case here, vegetable oils, like diesel fuels, like ethanol fuel source here, it can't be used directly in an internal combustion engine because they're too viscous. The viscosity, as we saw, actually depends on these chains here being very close together. So when I have all single bonds, although single bonds here allow for free rotation around, because they're all really parallel, the London forces will be really intense as you go along the chain. Even if you can unsaturate it, if you can pull off a couple hydrogens, make some double bonds, make some triple bonds, as you can introduce some of these kinks here, you see that the melting point themselves change really drastically. The chains can't pack together as nicely, and this will actually lower the viscosity as well. Chemically speaking, we've come up with a way to actually trade in esters. I can trade in one ester with an alcohol, trade it in for another ester and an alcohol in the presence of strong acid and strong base, and somehow I want to minimize this effect here of having this multiple long chains notion here. So transesterification, remember we learned ester formation condensing from an alcohol and carboxylic acid. In this case here, we're just making a trade. We have an ester and alcohol happens to be on both sides. Vegetable oils, unfortunately, have those 3 long fatty acid chains on the same molecule, on that glycerol. It's really hard to burn in a diesel engine. If I can trade in the react it in strong alcohol, I can shift the equilibrium over. I can trade it in for an ester, which are separate molecules. The long chain still has to go somewhere, but we're going to see in this transesterification process, we're going to take the fuel itself that has the 3 long chains on the same molecule. Upon a treatment here of either methanol or ethanol, I can even use Le Chatelier here because this is an equilibrium. I can increase the amount of alcohol, and I can actually shift this equilibrium to the right-hand side. We end up trading in the R group. We prefer the alcohol to have a short chain because that CH3 group gets added on to the chain itself. That's the CH3 we're seeing instead of the glycerol, but sort of not super clear here. As you notice, those CH3s now are 3 independent long chains. They're not 3 long chains that are stuck on the same glycerol. So by trading in that ester, by transesterifying this one here ends up becoming less viscous and a little bit more convenient for use. So that's using biofuels, lessening the dependence on regular fuel sources. Then back to our sort of photosynthesis analogy here, we talked about semiconductors. Semiconductors are sort of intermediary between insulators and conductors. Everything has what's called a band gap. Electrons typically occupy what's called the valence band down here. The band gap is the separation, the amount of energy that electrons or other charge carriers need to take to get into the conduction band to be able to be charges that can move around to actually conduct electricity. For an insulator, the band gap here is humongous. Those electrons on the bottom have a really hard time jumping upwards. Metals are sort of neck and neck. They're so close together. A semiconductor is sort of in the middle. So metals here, They generally have low ionization, really easy to promote those electrons. Silicon is our standard semiconductor. This one here is a medium band gap. Diamond would be an insulator. The electrons are really stuck in those sp3 bonds there, so not very conductive. We're going to compare semiconductor conductivity to metal conductivity. So metals generally have delocalized electrons. The positive nuclei themselves are stuck in place. Metals generally have the largest radii in the row. They have the lowest Z effective because the charges can very easily swim through the positive structure because of that delocalization. This one here is conductive. As you heat a metal, however, we're just increasing the amount that the vibrations are going to take. Electrons are going to bump into these positive nuclei a lot more. Because of that increased vibration, we're actually going to cause the conductivity to decrease. Semiconductors, in contrast here, at first when you're at low temperatures, not a lot of electrons can jump that band gap. They can't jump into the conduction band to conduct. However, as you increase the temperature, you're actually increasing the amount of electrons that have energy to actually go up into that conduction band and therefore conduct electricity. Better yet, we can actually dope the semiconductor. The silicon here is group 14, so it has 4 valence electrons. We can dope it with group 15 or group 13. The group 15 here will end up having 1 extra electron. They have 5 electrons where silicon only has 4. Those extra electrons will make the semiconductor an N-type semiconductor. I have electrons as extra charge carriers. I can dope it with small amounts of group 13 as well. Group 13 here has a bunch of holes. Basically, because they only have 3 out of the 4 valence electrons, electrons very quickly try to fill up those holes there, and basically we can think about them as positive holes that actually move around. So for N-type semiconductors here's just pure silicon. You don't need a lot of dopant, but hopefully there can be interspersed through the entire lattice itself. That added electron now provides extra electron carriers that can be promoted into the conduction band that can increase conductivity for us. Compared to the P-type semiconductor, like boron here, I want it to be similar in size because it only has 3 out of the 4 electrons here. Electrons can very quickly fill up that hole there, but leaving behind a hole, and we can actually see holes are positive charge carriers that can also move around, migrate through. What we can do here is we can actually couple the P and the N-type junction together. So here's the N-type, it has an excess of electrons. Here's the P-type with a lack of electrons or an excess of holes. Electrons at first naturally migrate over, filling out the positives. The positives go over to the negative side. We're going to end up creating what's called the depletion layer. Because all those electrons that are mounted on this side of the barrier, we're going to create a negative side. The holes went to the top, so the positive side here. If I then release extra free electrons, although I might want to go to the positive on my side here, there's an electric field set up that makes me no longer want to cross over to the other side. That charge buildup here is called the depletion layer, and basically we've cut off the natural migration, the natural meeting of electron and positive hole. What we then do here is we hook up an external circuit for a photovoltaic. Basically, we allow a detour around. If the electrons don't want to go through the depletion layer, they can actually go through this external circuit itself. The electrons are blocked by the depletion layer, but they can be routed through. This is going to be direct current because the electrons are flowing all in one direction, and we can taper off the electrical energy on the electrical circuit. Solar panels are essentially arrays and arrays of this photovoltaic. Right. So we can actually couple one after the other, and then we actually can mimic directly what photosynthesis does here is with a DSSC. We're going to take a dye that mimics what chlorophyll does. The dye has a conjugated structure. It absorbs all that solar radiation. The dye is sprayed onto TiO2 nanoparticles. The nanoparticles here have a really high surface area. That forms the anode. We end up releasing a lot of electrons. Naturally, there's a depletion layer here. Those electrons don't want to go through the charge buildup on this side here. But by providing that electrical circuit on the outside, we allow electrons to flow from the anode to the cathode, getting reduced down to complete the circuit. So the dye molecules here, instead of chlorophyll, actually absorb the light. They become D star. As they form D star, they get ionized, they become D plus and electron. The electrons get passed over to the TiO2. They excite the electrons in the TiO2 into that conduction band, and those electrons in the conduction band are actually the ones that actually migrate over to the cathode side. They travel through the external circuit here, they flow to the other side, getting reduced, but we've been able to already harness that electrical energy on the side here. On the other side here, we typically have triiodide that actually ends up reducing and picking up those electrons here. In the biological case here with photosynthesis, there's a very fancy electron transport chain. In this case here, our electron transport chain is analogous to electrons moving from the conduction band of TiO2, migrating over, being able to taper off that electric energy already, and then migrating over to the thing that actually gets reduced. In this case here, the thing that gets reduced are the triiodide ions. The triiodide grabs those extra electrons, reforming I minus. The D plus that was ionized previously can actually be reduced by this I minus subsequently here, and then it ends up reforming the dye itself. So we're basically mimicking a biological system to try to harness that electrical energy there. Here's another picture of the dye-sensitized solar cell here. Sunlight or concentrated interior light here. This is just dye sprayed on top of TiO2. With the nanoparticle design here, there's a lot of surface area. This improves the efficiency of the DSSC. As the electrons flow through that circuit there, we manage to taper off the electrical energy. The advantage of a DSSC versus just a generic photovoltaic, we talked about that high surface area. It's typically cheaper to manufacture. The efficiency of a typical voltaic, a solar cell here, actually decreases as it gets hot in the sun, and a DSSC can be used to work in low light conditions. Last couple slides here, we're going to look at the environmental impact, sort of global warming here. We talk about greenhouse gases. Greenhouse gases typically allow solar radiation. It's typically shorter wavelength. That radiation can get through, and when the solar radiation actually reflects off the Earth, it's usually reflected at a longer radiation. In this case here, the greenhouse gases absorb this radiation and then re-radiate it. We use that terminology instead of reflect it back, so re-radiate it back to the Earth. Again, what's important for you to note here is this greenhouse effect here. We talk about solar radiation, terrestrial radiation. This one here is a natural effect. Naturally, our atmosphere, most of it lets solar radiation through. It's just that there are gases in our atmosphere, CO2s and waters, that are normally there. They can actually absorb some of that terrestrial radiation and actually point some of that radiation back towards the Earth's surface. As this sort of cycles back and forth, it's a consequence that's resulting in warming the Earth. So in this case here, we're going to have, it is a natural phenomena. It allows our planet to keep an average temperature about 15 degrees. It allows us to sustain life. Most of the radiation is transmitted through the atmosphere. Most of the terrestrial radiation ends up getting re-radiated back to the Earth's surface. So these are some greenhouse gases. Right? Everyone has a different ability to actually re-radiate their radiation. So we can talk about greenhouse gases. This is believed to cause global warming, a gradual increase in temperature over the last thousands of years or so. We could also have particulate matter, so smoke and dust and polluted clouds, things like that. That can actually reflect some of the solar radiation, not actually let the solar radiation come in. That can actually cause, in a couple of years, we have global cooling, or a process called global dimming. So here's just a satellite image of our atmosphere. This is a global problem, so even though we're burning fossil fuels in a lot of first world countries, the atmosphere, the wind pattern just blows the carbon dioxide all around the world. This is going to take a global solution to actually address. What's important to note here is the chemistry behind how do these molecules like CO2, like water, how come they are IR sensitive? How come they are actually absorbing the thermal radiation to begin with? First thing we talked about in the spectroscopic chapter, we can think of bonds as little springs. They're constantly vibrating, bending, stretching. There's a couple of more interesting modes like wagging, rocking, things like that. Anytime I have these springs here, anytime a polar bond exists, there's a dipole moment. Even though the molecule CO2, the dipoles cancel out, overall we're nonpolar, having this dipole moment where oxygen is kind of negative, carbon is kind of positive, the spring here is constantly stretching and contracting here. As the IR radiation is of the right energy, it can actually cause this slinky here to actually stretch and contract a little bit more, bend a little bit more as well. And in that case there, it can the vibrational mode here will increase for a little while. Once it gets bored, it sort of goes back into the lower energy state here, and then it re-radiates that energy back to the lower energy state. So it is this change in dipole moment, that's an important way to describe it here, that actually allows it to absorb IR radiation. Greenhouse gases absorb this IR radiation, it excites those modes, it stretches, vibrates a little bit quicker, and then it re-emits this radiation back when it relaxes. So we just track the global atmospheric CO2. Again, CO2 is naturally in our atmosphere here. It's just that over the last 100 years or so, we see a steady increase, and this one here isn't coming downwards. as you plot that CO2 trend here versus the global temperature increase as well, as the CO2 has gone up, even though there are seasonal variations in temperature, so the global warming pattern there, we see that the temperature seems to correlate well with the CO2 concentration. And the worry, even though naturally CO2 normally gets formed, the worry is we're anthropomorphically creating more CO2 than normal, and therefore leading to global temperature increases. These studies here look back at ice core measurements of CO2 even hundreds of thousands of years ago, and there generally looks like there's a nice correlation between what the CO2 concentration was in the atmosphere and the global temperature at that point there. Our models so far, definitely different models themselves. We worry about the global temperature increasing because we're burning so many fossil fuels of late. The question here is whether the global warming will actually increase. Most of the models we have seen so far, they factor in many different variables here, but most of them lead to this increase in trend. And it doesn't take much. It can just be an increase of 1 degree, 2 degree, and they can have very devastating consequences on our biodistribution. The major greenhouse gases, I want you to say the most abundant one is actually water. However, its global warming potential is actually just 0.1. We need 10 water molecules to have the same impact, to have the equivalent impact of carbon dioxide, which has a 1. Methane, dollar for dollar, it's 30. However, we don't have a lot of methane produced from intensive farming. The overall contribution here is expected to be less. So depending on how you're framing it, you might say one greenhouse gas is worse than the other. What are some of the consequences here? We'll look at ocean acidification. Definitely with the melting, it'll cause an increase in sea level. It changes a lot of the biodistribution ecosystem patterns, and this is believed to cause more frequent extreme weather as well. So I have CO2 in the gas, I have CO2 in the aqueous. We're going to learn that normally there is a heterogeneous equilibrium. Heterogeneous because there's two different phases here. Heterogeneously here, CO2 should be able to dissolve in water, and CO2 here, because of this equilibrium, it's going to act as a carbon sink. It's going to sort of control how much CO2 is actually in the gas. However, upon global warming here, as the temperature increases, the CO2 is less and less soluble. The capacity for CO2 to actually soak up this CO2 here actually decreases. So therefore, we're going to have a net increase of CO2 in the atmosphere, and that's causing that absorbing IR radiation, re-radiating, causing that worry of global warming. Another impact of this one here, with sort of the limited impact of a carbon sink here, is if we manage to have more CO2, let's say we're cool enough here, we manage to dissolve more CO2. However, with CO2 in the waters, because it is a non-metal oxide, as it reacts with water, it forms carbonic acid. Carbonic acid is a weak acid, ending up releasing up H+ in the surroundings. We talked about here warming as sort of melting polar ice caps, ice deposits. That water as a liquid expands. It takes a little bit more volume. The sort of average sea level here is expected to rise here. Here's a nice picture of it. Within the last maybe 5-10 years or so, we see that it's increased by maybe a couple centimeters or so. And the worry is if we continue on this trend here, maybe the sea level will rise even more, resulting in more flooding cases, maybe cases that are close by sea level, even at risk of just going under completely. It's not all doom and gloom, however, here. If CO2 is the primary thing that's causing global warming, we can actually try to control our CO2 emissions. We can try to design our cars to be more efficient. So basically, I don't need to burn as much fuel, release as much carbon dioxide. If I can rely on more alternative sources, renewable sources, it decreases my dependence on gasolines. I can do sort of market-based control. I can put taxes on carbon here, or I can do something called sequestration. Sequestration is just a fancy word for capturing that carbon. Sometimes we have sort of little scrubbers here which can actually absorb that carbon, maybe keep it in carbon solid, that form there, actually keep it as just in that solid form, so therefore it never actually makes it into the CO2, makes it into that global warming potential. Last part here, we look at that as some electrochemical cells here. It does rehash a little bit of the redox chemistry, rehashes some terms like anode, cathode, electron flow, salt bridge, things like that. But primarily here, we're just doing a broad stroke, and we're looking at some common designs. I'll just show you a few last pictures here. Half reaction like this, we have electrons arriving here. That means this electroplate here is the cathode. The copper ions here swim up close. They grab the electrons. The site of electrons being reduced is called the cathode. They solidify on the surface, so this mass here would increase. This is only half cell, however, when we look at those electropotentials, they're all related to the standard hydrogen cell. That was called 0. this cell here will either oxidize or reduce better than hydrogen, and the voltage shown is the reduction potential. As you start putting this into actual battery design, we're going to learn that it takes a little while for electrons to actually travel through the battery itself. We're going to amount that to an internal resistance. There was a true amount of voltage that your chemical reactions were supposed to produce, but because it's taking a finite time for your charges to actually migrate and diffuse through this internal resistor, it's actually going to decrease some of that overall voltage. The terminal voltage is actually a little bit less than the EMF. Here's our standard electrochemical cell. See if you can identify all the bits. Electrons always flow anode to cathode. We did a slight modification in this section here. Basically, we've been doing standard state. We've been assuming everything was 1 molar, 298 Kelvin, 1 bar, and all that. But as the battery actually runs out, the chemical proportions actually change. There actually is a correction term that actually slowly says the voltage of the battery steady dies off as the amounts actually die off. We looked at a few common designs here. This is our car batteries. We have lead and lead 4 oxide here. They're both going to form PbO2 during the discharge cycle. PbSO4 is actually a solid. It's actually a coating that actually surrounds these plates here. During the discharge, that solid then forms. If I then jumpstart the battery or recharge the battery, I'm basically converting the PbSO4 back into the PbO2, Pb, allowing for fresh electrode surface, allowing for the battery to run again. Your cars are actually designed as they're running to constantly being recharging the battery. It's just that if you leave the battery over long periods of time, it might end up becoming a dead battery. So here's those reactions again. Make sure you can do oxidation number and identify who gained electrons, who lost electrons, in identifying the overall reaction. We compare that to the couple other batteries. AA batteries are probably nickel-cadmium designs. So we have the discharge, so going one way. These are all rechargeable. So if I run the reaction going the opposite way, it's not perfect, but as I replenish the amount of chemicals, I'm now ready for it to react again, ready to spontaneously generate electrical energy. We talked about lithium-ion cells first. So lithium-ion batteries here used for a lot of cell phones, things like that. Lithium is nice because it's relatively low density. It produces a lot of energy per lithium. We have the electron on this side. In all these cases here, electrons are flowing through the electrical circuit itself. We're tapering off the electrical energy with that direct current, and we basically have the other side that's absorbing the net electrons that arrive there. Then we get to our fuel cell here. This is a hydrogen fuel cell. Lots of designs in trying to make a hydrogen fuel cell. It is going to need a continuous supply of hydrogen and oxygen. Hydrogen is flammable and explosive, so it's a little bit hard to store and transport and safely work with. However, if I can harness this continuous supply of hydrogen and oxygen, I notice the waste product out of this reaction, whether it's base catalyzed or on the next slide here acid catalyzed, the only product coming off of it is water. Very, very environmental. So again, we're able to force the electrons through a wire ring. We're able to carry that current. For the electric side here, we call this a proton exchange membrane. We play around with the substrate so that the H+ can naturally migrate over. But again, we're going to just be producing plain old water and very, very clean energy. So we have the reactions for it being under acidic conditions with the H+, or basic conditions with the OH-. And finally, what we're going to look at here is a sort of microbial fuel cell here. Fuel cells don't have to be just hydrogen and oxygen as a source. In this case here, we can put otherwise waste water. We can actually utilize microbes, microorganisms, bacteria. In an anaerobic environment, it can convert some of this waste matter. It can actually cause the loss of electrons. Those electrons get oxidized and the electrons travel to the other side. On the other side, we are using oxygen as a source, so definitely going to be aerobic. But as long as something is willing to reduce and gain those electrons, we've allowed electrons to flow through the circuit. And again, we've been able to taper off that electrical energy. So hopefully that's a nice overview of this option here. You will need to look back into section by section for some of the details, but hopefully it just introduces to you what this option was about. Thanks guys, take care.